Okay, so good morning. So today's chemistry lesson, you guys are going to watch this video and I want you to pause it and take notes, add them to your notebook. And also as we go through a few example problems, you should pause it and see if you can answer the problems before I give you the answers. Okay, so let's start. So today we're going to be talking about the mole. Not that mole. We actually mean the chemistry mole. So the mole in chemistry is a counting unit. All right, so it's similar to saying you want a dozen of something, except you're going to say you want a mole. So a mole is 602 billion trillion. All right, that's a little unwieldy. So we're going to use this number, 6.022 times 10 to the 23rd. All right, so we always use this in scientific notation for obvious reasons. And this is referred to as Avogadro's number. So Avogadro studied quantities of gases and discovered that no matter what the gas was, there were always the same number of molecules present. We'll actually come back to this a little bit later in this unit, but for now, just know that 6.022 times 10 to the 23rd is Avogadro's number. And this is something that you should memorize. All right, so as I said, the mole is a counting number, so you think of it the same way. We know a dozen cookies is 12. A mole is 6.022 times 10 to the 23rd. A dozen cars, 12 cars. A mole, 6.022 times 10 to the 23rd. A dozen aluminum atoms, 12 aluminum atoms. A mole, 6.022 times 10 to the 23rd. And obviously this is so big because aluminum atoms, when we start thinking about chemistry, are really small. So we need a big number so that this is something that we can actually measure and that makes sense for us to use. So note that the number is always the same, but the mass is very different. And we'll be getting back to that a little bit later. All right, and mole is abbreviated MOL. So pretty easy there. All right, so as we said, you should know probably already this number, 6.022 times 10 to the 23rd. So no matter what type of atom or molecule or ionic compound we have, if we have this many, it means we have a mole of each. So notice we can use this to refer to atoms or molecules. So your questions will usually be stated in how many atoms or how many molecules. All right, technically, sodium chloride is an ionic compound, so we don't technically say molecule, though a lot of times we slip and do. But notice these ionic compounds, when they dissociate in water, it means you have a mole of sodium and a mole of chlorine ions because these are present in a 1-to-1 ratio. Okay, so what happens though if we have something like calcium chloride? So now we have 1 calcium atom to every 2 chlorine ions. So how many moles of calcium are in 1 mole of calcium chloride? All right, that should be pretty straightforward, okay? But just so you start to think about this in dimensional analysis terms, we could set it up this way. You could say 1 mole of calcium chloride, and then here you look at the molecule. So for every mole of calcium chloride, it has a mole of calcium. Calcium chloride crosses out, and you get calcium for 1 mole. All right, similarly, if we want to know how many moles of chloride, we can start with 1 mole of calcium chloride, and now for every mole of calcium chloride, right, there's 2 chlorines, so 2 moles of chloride. So there's going to be 2 moles of chloride in every 1 mole of calcium chloride. Does that make sense? All right, let's add on a little bit. So how many moles of hydrogen are in 6 moles of NH3 or ammonia? All right, so now note you've got 1 nitrogen to 3 hydrogens. So if we set this up, you're going to start with 6 moles of NH3. All right, and then for every 1 mole of NH3, we're going to have 3 moles of hydrogen. All right, the moles NH3 cross out, and you're left with 18 moles hydrogen. Okay, now would be a good time to pause, if you haven't been doing this already, and see if you can figure out how many moles of hydrogen are in 0.5 moles of NH3. Okay, are you back with us? So this is how you should have set it up. 0.5 moles of NH3, you have the same conversion factor, and you get 1.5 moles of hydrogen. All right, and that kind of makes sense because if we multiply 0.5 by 3, we get 1.5. Okay. All right, so how do we use Avogadro's number in all this? So what we can do is it can give us two conversion factors. So we can either put the Avogadro's number on top and mole on the bottom, or mole on top and the particles on the bottom. Okay, so for every 1 mole, remember we have 6.022 times 10 to the 23. And here we're just saying particles. That could be either atoms or molecules. All right, so let's test this out. Okay, so check your dimensional analysis skills. Pause the video here and see if you can do these questions. Okay, how did you do? All right, if you're having a little trouble, here's how you set them up. So you start with 0.5 moles. So here's our 0.5 moles of aluminum. And now since this is on top, we have to use the conversion factor with 1 mole on the bottom and our Avogadro's number on top. Moles cross out and we multiply 0.5 times Avogadro's number to get our answer. Okay. And then here we start the opposite. We know how many atoms we have and we want to figure out moles. So now you use this conversion factor with the Avogadro's number on the bottom. So here our atoms can cross out and 1 mole on top. So now you're taking this 1.8 times 10 to the 24th and dividing it by Avogadro's number, and you should get about 3 moles. I think the answer that comes up on your calculator is probably like 2.98 something, but we can round that up to 3 moles. Okay? All right, so here, just some things to remember. The mass of 1 mole, so remember 1 mole is 6.022 times 10 to the 23rd atoms. What does that mean for mass? So it's equal to the numerical value of the average atomic mass. This is the number you get from your periodic table. Okay, so again, remember way back when in the fall when we talked about the average atomic mass? So that's basically the weighted average of all those isotopes. Ringing a bell? All right, basically what you need to know now is it's the number on the periodic table. All right, so if you look, pull your periodic table out. Go ahead and pause it for a second. All right, so you should be able to see that 1 mole of carbon atoms is 12 grams. 1 mole of magnesium atoms is 24.3 grams. 1 mole of copper is 63.5 grams. Okay, so do you see how those work? So we just convert that atomic mass unit that's on your periodic table, that just winds up being grams. Okay? All right, just a couple things that might crop up as you're doing these problems. You'll usually see those referred to as molecular mass or molecular weight. All right, occasionally you'll see formula mass or formula weight. So this is for ionic compounds that are technically not molecules. So sometimes they'll just be called formula weight. You may hear all of these. They basically mean the same thing. You're still going to go to the periodic table. You're still going to find the atomic mass. Okay, so here's a learning check. Pause it, look at your periodic table, figure out what the mass is of 1 mole of bromine atoms and 1 mole of tin. All right, so you should have found 79.9. All right, and we literally say this is 79.9 grams per mole of bromine. And we've got 118.7 grams per mole for tin. All right, what do you do in a compound though? Okay, so what you do is you separate the compound. You figure out how many of each type of atom there are. You look up the molar masses on the periodic table, and then you add them together. So here we have calcium chloride. That means we have 1 mole of calcium at 40.1 grams per mole, and we have 2 moles of chlorine because we've got the subscript here. So 2 moles, each mole of chlorine is going to be 35.5. So we multiply that by 2, add that to our 40.1, and that means that the molecular mass of calcium chloride is 111.1 grams per mole. So what this means is each mole of calcium chloride weighs 111.1 grams. Okay? All right, here's a learning check. So pause again, go to your periodic table, and see if you can figure out what 1 mole of dinitrogen tetroxide would weigh. Okay. All right, so you're back. Hopefully you got 92.0 grams per mole. All right, here's a couple, our last 2 learning checks. So again, pause the video, see if you can figure these out. Okay, if you're back, so this is basically what you do. We needed 2 potassium, so that's 39.1 times 2 gives you 78.3. We're going to add that to the molecular weight of oxygen, which is 16, and you should get 94.2 grams per mole. And then for aluminum hydroxide, we've got 26.98. Remember, the oxygen you have to multiply by 3. So remember, this is in parentheses. So that means we have 3 OHs. So you've got 3 oxygens and 3 hydrogens. Okay, and I think this is probably at the bottom of the screen, but you should wind up with 78.01 grams per mole. All right, so how did you do? Do you feel like you know what a mole is now? All right, so we'll be back with more things to do tomorrow. Have a great day.